everyone, and welcome to Tech Tuesday. As we wait for everyone to jump on here, I'll give a brief introduction. I'm Abby Weber, and I'll be your host today. I work on the marketing team here at FCT Solder, and for today's webinar, we are excited to be featuring a presentation put together by Tony Lentz, a field application engineer for FCT Solder. This is a reboot of a previous webinar on the topic of a novel solder paste to meet the challenges of the electronics industry. Tony is here with us today to help answer any questions you may have after the presentation. Today's webinar will be recorded and will be available to you through a link that you will get in your email tomorrow. There will be time for a Q&A session towards the end. You'll see the Q&A tab at the bottom of your screen, so feel free to throw any questions you have in there. If we don't get to your question today, we will be sure to follow up, or you are always welcome to contact us directly. Now let's jump right in.
Thanks everyone for attending today. We appreciate that. This presentation is about a novel solder paste which has been designed to meet the challenges of the electronics industry. First of all, let's talk a little bit about the evolution of electronics and where we're using electronic devices and where they're headed in the future. Of course, we've all heard of 5G. That's the new latest communication standard. That includes increased speed, better signal strength, of course, transferring large amounts of data in a fast, short period of time is the goal here. And we are definitely heading down the road of Internet of Things, where we're connecting more and more devices to the internet than we ever have before. For example, like kids' toothbrushes, so you can monitor how long and how often they're actually brushing their teeth. Or your refrigerator, so you can pull up a video of what's inside the fridge when you're at the store. If you forgot to buy that gallon of milk, you can go shop for that while you're out of the house, or turning on your lights while you're not home. I mean, it's amazing all the things we've got connected to the internet these days. So, of course, that demands greater technology in these communication and networking equipment. Global 5G adoption trends are also rising pretty dramatically. As you can see in this chart on the right, here in 2021, they expect roughly 600 million worldwide smartphone subscriptions that are 5G capable. And in the next 5 years, that's going to go up to over 3,300 million subscribers. That's a huge increase in 5G usage. And with that increase, of course, comes all the hardware that's necessary in order to make that work properly. Here's a couple of trends for microprocessors and transistors on microchips. And so this chart on the left is 42 years of microprocessor trends from 1970 up through 2020. And if you just look at the orange triangles here at the top, you can see the number of transistors in the thousands has increased dramatically since 1970 in their inception. You know, you might have had 10 on a microprocessor. Now we're looking at 100 million or 100 billion. It's amazing how much technology we're cramming into our electronic devices. And with that, of course, comes increased density of the electronic device. We're cramming a lot more components with higher functionality into a smaller footprint. And then on the right, we've got a chart showing Moore's Law, which is the number of transistors on a microchip doubles every 2 years. And this ranges from 1970 to 2020. And you can see the increase on this as well. It pretty much follows the microprocessor trend data. So the point is that we are demanding more of our electronics and putting more electronic devices in more places. So that requires a lot of circuit boards to be built. And these circuit boards are quite often very challenging. And they're challenging for solder paste, they're challenging for component suppliers, and for all of us who are involved in supplying to that industry. So here are some of the challenges that we face when building these type of electronic devices. First of all, we're using larger BGA components than ever before. The size of the BGA components is increasing, which unfortunately gives more functionality, which is good, but it lends itself to potential problems of warpage-related head-on-pillow. Voiding is a potential issue in BGA spheres, like what's pictured here in the bottom. So there are definitely issues that come along with using larger, more highly functional BGAs. We've seen the adoption of bottom terminated components. They're pretty widespread. And unfortunately, bottom terminated components, just because of their physical design, lend themselves to voiding in solder joints, which can create its own problems with the function of that circuit board. And then we're also putting electronics into potentially harsh end-use environments. For example, electronics that are stored outdoors or under the hood of a car or even in space. Those are fairly harsh conditions under which that electronic device has to function properly for its life. And therefore, the reliability of the circuit board is key. And thermal cycling is one potential issue from that, especially if you've got a circuit board outdoors. It's going to be cold in the winter and warm in the summer. And then when that device is powered up, of course, how hot does it really get? But those things can potentially lead to solder joint failure. And then one of the other challenges that we face is circuit board designs. We see a lot of mixed technology designs where we've got large thermally demanding components like these heat sinks here on this picture on the right, placed directly right next to smaller passive chip components like these guys over here. And so you've got different thermal demands for reflow profiling that circuit board. It makes it very difficult, as well as different solder paste volume requirements. And so these are some of the challenges that we face building these type of electronics. And of course, the solder pastes have to meet those challenges. Here are a couple of challenges that come along with telecom and network infrastructure electronics. I talked a little bit about harsh environments. Well, think about the environment in space for a communication satellite. That circuit board has to be pristinely clean, sealed, and able to function without being damaged by the radiation or exposure to the vacuum of space. And then also, I would think of this communications tower as a harsh environment. It is outdoors, subject to temperature extremes, and also wind, rain, snow. All types of environmental effects could occur to cause those circuit boards to fail at some point if they're not protected properly. And then of course, what about the theory that 5G causes viruses like COVID-19? Now, I don't have an opinion on that. I just present that as an interesting idea. Well, I'll let you all decide whether that plays a role or not. Certainly, when we formulate solder paste, we can look at all of these things, and we want to try to meet these challenges with our solder pastes. Here's a little more information on BGAs and why they warp and how that leads to head and pillow. So BGAs are, like I said, are increasing in size. I've seen BGAs in use of up to 2.5 inches square, which is fairly large. And they're testing BGAs upwards of 80 to 85 millimeters. So that's almost 3.5 inches square. That's a huge component if you think about it. And all those solder spheres on the bottom of that component have to make proper solder joints. Well, during reflow, BGAs tend to warp, like what's pictured here. So during the soak or the ramp up part of the profile, you can see this BGA diagram. It's warping up off of the circuit board, and it's pulling some of the solder paste with it, or completely separating from the solder paste. And then once the solder goes liquid, the balls will melt individually and the solder paste will melt, and it's not in contact with the sphere of the BGA, and therefore they'll never merge together properly. And so when that component cools down at the end of the reflow profile, you've got this situation where you've got the sphere and the pillow of the solder paste just separate from each other with a dividing line. And that may or may not be making electrical contact. So that's definitely a source of failure with using larger BGAs. And larger BGAs are more susceptible to that problem because the larger they are, the more warpage induces curl or potato chipping in that component. Bottom terminated components are obviously commonly used in our industry. We've got a picture of a QFN here that's pretty standard. There are DPACs and then also QFPs with a thermal pad on the bottom. Of course, with these comes the challenges of how to get the right amount of solder paste in order to make a solid connection to all of those contacts, especially the larger plane areas like what's pictured here. So this is an example of 3 different ways to print solder paste onto the thermal pad of that QFN. These are all 70% area of coverage, and it's just 3 different theories on how to break that paste up. But the point is you can see how large the ground plane part of that component is compared to how much paste you have to put down. There's a relatively large amount of paste going down there. And when that paste creates volatile gases during reflow, those gases can't escape out of the top because the component is flat, and it basically prevents the gases from moving to the top of the solder joint like they would naturally want to do due to the relative densities of the solder versus the gas. So the gases have to try to escape out the side, which is a relatively long trip from the center of a QFN to the edge. So that tends to lead itself to voiding. And so the solder pastes that we create have to be created with respect to minimizing voiding potential for these types of components. Voiding can lead itself or lend itself to these types of failures. There's potential for overheating failure, like what's pictured here. One of these D-packs overheated and actually burned the circuit board. And I don't know if that was specifically due to voiding, but that's certainly one potential. If there's large amount of voiding in that thermal solder joint, then the component's not able to wick heat away quickly enough, and this could happen. The BGA sphere on the right shows a void-induced crack. You can see that void is actually fairly large compared to the BGA sphere, and it definitely cracked at some point in its life. So voids can definitely cause some problems in solder joints. What about harsh environment and the reliability of solder joints? I was talking a little bit about electronics that are used outdoors, where here's an example of winter versus summertime. The air temperature could range from, say, -40 centigrade to +50 centigrade in extremely hot climates. But the board surface itself probably will get down to -40 centigrade based on whatever the outdoor winter temperature is. But when you power that up and it generates some heat from its use, it could easily get up to 125 C or higher, which is why we use that temperature range for reliability testing quite typically. But with that thermal cycling over a period of time comes fatigue, and eventually the solder will crack, or the different coefficients of thermal expansion between the component, the solder joint, and the board surface just eventually induce cracking in solder joints. And so that's one potential problem for electronics that are used outdoors or in harsh environments. Different component sizes that we use on mixed technology boards also create some challenges. Like I mentioned earlier, we've got a fairly large component here versus some pretty small components which have totally different solder paste volume requirements. The large component requires a lot more solder paste. And when you reflow that, this large component is going to act like a heat sink. And so it can be quite challenging to get the appropriate reflow temperature for the solder paste underneath the larger component, as opposed to trying not to overheat the solder joints on these smaller passive chip components. So a couple of things we can do to help with that are use of step stencils. If we use a step stencil, we can obviously increase the volume with a step up in a certain area. But as soon as you increase the thickness of the stencil, you have effectively reduced the area ratio of those apertures, which may present a printing challenge for the solder paste. And then the same holds true for the thermal profile. You can obviously use a soak profile, give it a really slow ramp up to peak in order to heat up all of these components equally. But not all solder paste can handle a long, hot soak profile. And so when we formulate new solder pastes, we have to think about these things. We have to make sure that can print through a wide range of area ratios, as well as handle a wide range of different profile conditions. So here's some information about a new solder paste that we worked on in order to meet these challenges. The requirements that we used specifically for this solder paste, besides what I've already mentioned, we want to make sure this solder paste has some potential to reduce head and pillow. And we did that through increasing the activity of the solder paste, which helps to remove oxides on the BGA sphere, as well as within the solder powder itself. That helps to ensure that these solder deposits will merge properly during reflow. We can adjust the rheology of the solder paste, making it a little more elastic so that it will stretch. So if a BGA warps and pulls the sphere up out of the paste deposit, the paste will have more of a potential to stretch along with it and stay in contact with the BGA sphere rather than snapping back to the board surface. And then we also want to make sure the solder paste can handle a wide thermal profile window, like I mentioned on the last slide, so that we can minimize warpage in BGAs by using a soak type profile in order to slowly heat things up and hopefully the BJs don't warp as aggressively under those reflow conditions. In terms of voiding reduction, we formulate solder paste in order to minimize the potential for voiding. Obviously, there are a lot of different sources of voiding that can range from the circuit board materials to the component surface to the board design. There's so many things that influence voiding, but the solder paste, as I've always said, sets the baseline for voiding potential. And so we try to minimize that voiding potential by using higher activity in the solder paste to remove oxides and to promote wetting and flow. So the voiding is caused by two major things. Either the solder paste doesn't wet and flow completely and leaves a gap in the solder joint, either at the component interface or the board pad. And that, by its very nature, that gap in the solder joint is a void. And the other thing that solder pastes do is they create gases during reflow. And so we can switch the solvents and use different rosins that specifically minimize gas generation during reflow. And together, those solder pastes can then produce very low voiding levels compared to what we've seen in previous generations of solder paste. In terms of reliability, there's a couple of things we do with solder paste formulations. The first thing is we try to make them halide and halogen free, especially for no clean fluxes, so that there is no potential halide or halogens on that surface, which could potentially corrode or cause dendritic growth to the metal surfaces. We also want to make sure these solder pastes pass all of our industry standards for SIR and ECM, including IPC J Standard 004, JIS 3197, and Telcordia GR78. And all of these test methods have different test criteria, slightly different circuit board designs. And so it's quite a rigorous set of tests, and that we ensure that new solder paste can meet all of these criteria and pass those tests very well, so that the flux is benign, at least as benign as it can be when you leave no clean flux on the circuit board surface. And then in terms of reliability of the solder joint itself, that's more of a matter of what the solder alloy is doing. And so in this particular case, I'm showing Inalot versus SN100CV. SN100CV is a new solder alloy, relatively new, that we're promoting in our solder pastes. And it was designed to give higher reliability test with certain types of tests versus things like Inalot. And so in this particular case, the blue dots here show the SN100CV Weibull plot, and it lasted longer through more cycles than Inalot did in this particular test. The other alloy that we are marketing for high reliability applications is called LFC2. Now, choosing high reliability alloys will definitely increase the solder joint life, especially for harsh environments. And if we're talking about like something that has to go into space or is outdoors or potentially under the hood of an automobile, you've got a lot of thermal cycling going on under the hood of a car and a lot of vibration as well. And so you have to use the right solder alloy for those conditions in order to ensure that the solder joints last as long as they're designed to. So the solder paste that we worked on also has to be able to print in a wide area ratio range. And so we've got an example here on the left of transfer efficiency versus area ratio. And these area ratios that we test normally range from 0.30 up to 0.80. And in this particular chart, we're showing three different solder powder types: SAC 305, Type 3, Type 4, and Type 5. And what we want to do with this test is see where the transfer efficiency minimum, or where the area ratio minimum is, that allows us to get 70% transfer efficiency. And so we formulate solder paste to print through lower area ratios and test them through this type of a test. And so we really challenge the solder paste by taking them all the way down to a 0.30 area ratio. The other thing we do is we run our solder paste through a wide range of refill profiles. And we use a variety of materials in the solder paste in order to help broaden this window for reflow profiles. So this particular reflow profile example is from J Standard 020. And it just shows you what's normally used in our industry. I mean, we have very short cool profiles ranging to long hot profiles. Sometimes we use relatively long soaks. Sometimes there is no soak and it's a linear ramp to peak. And we want to make sure that our solder paste can run in all of those profiles because they're all used in the variety of electronics that are built. Some other things that we look at for new solder pastes is we want to make sure they have good small deposit coalescence. That means they aren't going to create graping. So this is a test pattern that we commonly use, and the area ratios that we're printing through range from 0.35 up to 0.70 on these patterns. And the smaller patterns, by their very nature, tend to be more susceptible to graping because you have a very small solder paste deposit with a relatively large surface area of solder powder in the paste, which can oxidize during reflow. And the paste flux has to protect that from oxidation and have enough activity to remove the oxide so it coalesces properly. And so we always run this test as part of our R&D on new solder pastes. We also wanted any new solder paste to be pin testable. For anyone who's doing in-circuit testing or flying probe testing like this, we want the flux to be soft and pliable for at least up to 5 days so that circuit boards that are queued up after assembly can be tested later on. And then we want the solder paste to work with pin and paste applications. We still see our customers using this a fair amount. If you have, say, one connector on a circuit board and the rest of it is surface mount, it makes sense to try to use pin and paste reflow for that connector, for that through-hole soldering, if you can get away with it. So here's some test data on this novel solder paste. First of all, we run a print and pause test over a period of time. And so this particular paste was printed over an 8-hour window, and it has pauses of 1 hour, 2 hours, and then 4 hours during the test. We want to make sure that the solder paste transfer efficiency here doesn't drop off after any one of these pauses to make sure it's not drying out in the stencil. And so in this particular case, we have optimal printing over the 8-hour print and pause test. And then in terms of reflow performance, here's a comparison of the new solder paste, which is the blue bars, and a comparable solder paste, an older generation, is the orange bar. So wetting had much improved with the new solder paste, as well as solder balling and graping. All of these, higher is better on this particular chart. And so we were able to improve all of these reflow characteristics with the new solder paste formulations. And then lastly, we measure voiding with QFN components typically. And this new solder paste was designed to give ultra low voiding. And so we typically see voiding like this down below 2% void area on a 10mm QFN. So out of all this work, we created a new solder paste in our process amplifying series that we're calling AMP1 PT. That's all I have for this webinar. Thank you for your attendance. We really appreciate it. And now we have time for questions.
Awesome. That is a great presentation, Tony. Now let's see if we have any questions. What is the shelf life and how do you usually test that?
In terms of testing for shelf life, the real test would be to keep solder paste around under normal storage conditions and then test it after 9 months or 12 months, whatever the shelf life is declared to be. But we do an accelerated version of that test, so we don't delay release of that solder paste to the market by that period of time. So what we tend to do is we'll take solder paste in sealed containers and we'll heat them in an oven, either at 30°C, 40°C, or 50°C, or sometimes all different temperatures for periods of time, weeks of time. And we've estimated that heating forces sort of a premature aging of the solder paste. And we use that to help dictate what the shelf life will be.
Awesome, thank you. Does a high level of BGA voiding, size and/or frequency lead to a higher propensity for solder ball cracks?
I believe that it can, if it's high enough, certainly, and if the voids are concentrated at one of the interfaces. If the void's concentrated either the component interface or the board interface, then certainly you could have a weak plane within the solder joint that could crack. But I've also seen some papers and research on a low level of voiding or moderate levels of voiding in BGAs actually enhancing the reliability of the solder joint, because they act sort of like expansion cracks in a road that are intentionally placed there to help with thermal cycling. And so some level of voiding can actually be good for solder joints.
Awesome. What is the recommended stencil thickness for BCT devices?
That really depends on what else is on the circuit board. I know our stencil division says the most common stencil thickness is 5 mils. That's typical. I've seen people go down to 4 mil thick stencils if you're using like micro BGAs. It depends on how fine of a print you're trying to get to and what the area ratios that you're looking at. Obviously, we try to maintain area ratios above 0.66, which is the IPC recommended minimum. But sometimes you might run into areas where that's not possible. And in that case, we'd recommend step stencils to help with that.
Great, thanks for your insight on that. We are a low volume user, but we are still interested in high reliability solders. Is this paste stable for repeated use day after day?
Yes, we actually do a test where we will run pastes day after day for typically 5 to 7 days in a row, simulating low volume usage. And this paste is very stable under those kind of conditions.
Great. I saw you answered this one in the chat, but I'll just read it out loud as well. Is the flux cleanable as well?
Yes, this particular flux is cleanable, as are all of our no cleans, assuming you're using the proper cleaning chemistry to do that work. And we don't manufacture or sell cleaning chemicals, and instead we defer to the experts like Zestron and Kaizen and those type of companies. We recommend that you get in touch with your preferred cleaning supplier for the right cleaning chemistry for your needs. Because it's not just this solder paste you'd be cleaning, I'm assuming. It's probably also whatever flux you're using for touch-up and rework. Maybe you have wave fluxes in the building or selective soldering flux, and you might be cleaning other things off that we know nothing about.
Sounds good. Is this paste available now?
Yes, it is. It's actually been on the market for about a year, I believe.
Perfect.
Are there any other questions?
Well, if there are no more questions, we'll start wrapping things up. Thanks again for that great presentation, Tony, and being here with us again today.
You're welcome. Thank you everyone for attending. We appreciate you taking the time to listen to this presentation. And if you do have follow-up questions after the fact, you can always give us a call or email me directly. My contact information is on our website and also on this presentation.
Awesome. Yeah, thank you everyone for your attendance and participation. And just as a reminder, this webinar was recorded and you can access it through a link that you'll receive in your email tomorrow. As we mentioned before, don't hesitate to reach out. Be on the lookout for future topics, and we look forward to seeing you in October for the next Tech Tuesday. Have a great rest of your day, everybody.